For more than a century, our picture of the universe has been built on a simple assumption. The farther we look into space, the farther we look back in time. Every additional billion light-years becomes another chapter in a history we cannot replay. The earliest galaxies were expected to be small, chaotic collections of newborn stars, still assembling themselves from the debris left behind by the Big Bang. That expectation was not a guess. It emerged from decades of observation, increasingly sophisticated computer simulations, and a cosmological model that has explained an astonishing range of phenomena. The expansion of space, the pattern of the cosmic microwave background, the distribution of galaxies across billions of light-years, even the abundance of the lightest elements all fit together with remarkable consistency. The model was never expected to answer every question about galaxy formation. Astrophysics is complicated. Gas cools, stars explode, black holes inject enormous amounts of energy back into their surroundings, entire galaxies collide and merge. Even so, the broad sequence appeared reliable. Small structures should form first. Larger systems should emerge gradually as gravity assembled matter over hundreds of millions of years. Then the James Webb Space Telescope opened its mirror. Almost immediately, astronomers began seeing galaxies at distances that had previously belonged more to theory than observation. These were not simply faint points of light, extending the cosmic record by a little farther. They appeared unusually bright. In several cases, they also appeared unexpectedly massive. If those first measurements were correct, something had reached maturity astonishingly quickly. At first, almost nobody interpreted this as evidence that the universe itself had been misunderstood. There was a simpler possibility. Distance estimates at extreme redshift are difficult. Dust can imitate greater distances. Young stars can produce colors that resemble much older populations. A single misleading spectral feature can place a galaxy billions of years earlier than it truly belongs. Astronomers have experienced similar moments before. Promising discoveries sometimes become ordinary after better measurements arrive. So caution came naturally. The first response was not excitement, it was verification. Spectroscopic observations became essential because they measure precise fingerprints of atomic transitions instead of relying primarily on broadband colors. Several dramatic candidates did not survive that scrutiny. One object initially believed to exist at an extraordinarily early epoch turned out to be much closer, its light altered by dust and emission lines in ways that had fooled earlier analysis. That correction was reassuring. It suggested that at least part of the apparent crisis reflected the normal process of learning how to use an entirely new observatory. A nature, but reassurance did not last long. As more spectra accumulated, several extraordinarily distant galaxies were confirmed rather than rejected. Some existed when the universe was only a few hundred million years old. Others pushed beyond redshift 14, placing them astonishingly close to the beginning of cosmic history. Their existence was no longer an artifact of uncertain measurements. They were real observations anchored by spectroscopy that did not automatically overturn cosmology. Instead, it created a more subtle and more uncomfortable problem. The telescope had answered one question while opening another. The galaxies existed. Now researchers had to explain how they became what they appeared to be. Brightness alone is deceptive. A compact burst of star formation can briefly make a galaxy appear far more luminous than its total mass would suggest. Estimating stellar mass requires interpreting the combined light of millions or billions of stars whose individual properties cannot be separated at those distances. Those estimates depend on assumptions about stellar populations, dust, metallicity, and the history of star formation itself. Change those assumptions, and the inferred mass changes as well. That realization shifted the debate. Perhaps the galaxies were not impossibly massive after all. Perhaps astronomers had simply underestimated how uncertain those early measurements really were. Recent analyses argue that systematic uncertainties, selection effects, and statistical biases can significantly reduce the apparent conflict between these observations and conventional galaxy formation models. In some cases, galaxies that originally seemed almost impossible become much easier to reconcile once those uncertainties are treated more realistically. AAPS Journals 3. If that explanation proves sufficient, then Webb has not broken cosmology. It has exposed weaknesses in the methods used to estimate the properties of galaxies at the very edge of observation. But the conversation did not end there, because even after accounting for those corrections, another pattern remained difficult to ignore. The earliest universe does not merely contain isolated surprises. Again and again, Webb has revealed systems that seem to grow rapidly, assemble stars efficiently, and organize themselves earlier than many researchers expected before launch. Reviews of the first years of Webb science describe an emerging picture of vigorous galaxy growth throughout the first billion years rather than isolated anomalies waiting to disappear. That distinction matters. One unusual galaxy can be dismissed as luck. A growing population demands explanation. And this is where the investigation becomes more unsettling than any single image released by the telescope. Because the real question is no longer whether one galaxy appeared too early. The real question is whether our timeline for how complexity emerges in the universe has been quietly incomplete from the very beginning. If the earliest galaxies formed faster than expected, then every assumption built upon that pace, from the birth of stars to the growth of black holes, and eventually the appearance of planets capable of supporting life, may need to be reconsidered. Not abandoned, reconsidered. That difference is easy to overlook. Science rarely collapses overnight. More often, it survives by revealing that its strongest models contained uncertainties large enough to hide an entirely different history. And Webb may be showing us that the first billion years after the Big Bang were not slower than we imagined. They may have been far more efficient than we ever learned to expect. One of the most persistent misconceptions about the James Webb Space Telescope is that it has already disproved the standard model of cosmology. That conclusion travels quickly because it is simple. The evidence is not. The more difficult story begins with an uncomfortable observation. Cosmology and galaxy formation are not the same problem. The expansion history of the universe can be measured independently through the cosmic microwave background, baryon acoustic oscillations, supernovae, and the large-scale distribution of galaxies. Those measurements have repeatedly pointed toward a remarkably successful framework known as Lambda cold dark matter, or LCDM. Within that framework, the universe is about 13.8 billion years old. Dark matter provides the gravitational scaffolding for structure formation, and ordinary matter gradually settles into those invisible halos to produce stars and galaxies. JWST has not directly contradicted those measurements. Instead, it has challenged the assumptions about how efficiently ordinary matter assembled itself within that framework. That distinction changes the entire investigation. Imagine constructing a detailed map of a city's road network. The roads, intersections, and distances are all measured correctly. Months later, someone discovers that traffic moves twice as efficiently through the city as every transportation model predicted. The map remains accurate. The behavior taking place upon that map does not. That is roughly where astronomers now find themselves. The earliest galaxies seem to have converted gas into stars with remarkable speed. Some contain unexpectedly evolved stellar populations. Others appear surprisingly organized instead of resembling loose collections of scattered, star-forming regions. None of those observations immediately require rewriting cosmology. They require explaining astrophysics operating under conditions humanity has never observed before. The first generations of stars may hold part of the answer. Today's stars form from gas already enriched by billions of years of stellar evolution. Earlier generations lived in an entirely different chemical environment. The first stars likely formed from almost pure hydrogen and helium, with virtually none of the heavier elements that modern stars inherit from previous generations. That difference affects everything: the cooling rate of gas clouds, the masses of newborn stars, the intensity of ultraviolet radiation, the timing of supernova explosions, even the amount of ionizing light escaping into surrounding space. Many simulations before JWST necessarily relied on assumptions about these processes because direct observations simply did not exist. Researchers could test those assumptions only indirectly. Now, for the first time, they can compare them against galaxies that actually existed during those earliest epochs. Some of the comparisons have been reassuring. Others have exposed unexpected weaknesses. Several simulation groups have demonstrated that relatively modest adjustments to star formation efficiency, gas inflow rates, stellar feedback, and the treatment of dust can produce a galaxy resembling many of Webb's discoveries without abandoning LCDM. The challenge is not whether such galaxies can exist at all, but how frequently they should appear. Current work increasingly focuses on population statistics rather than isolated objects. That shift may sound technical, yet it carries profound implications. Science rarely breaks because of one surprising observation. It changes because an entire statistical pattern refuses to disappear. Suppose one person wins a national lottery. Nobody questions probability. Suppose 10,000 people win the same drawing. Now probability itself becomes the investigation. Astronomers have entered that second stage. Each additional deep field survey slightly changes the statistics. Each confirmed high redshift galaxy strengthens or weakens competing explanations. The debate has become less about individual discoveries and more about the overall pace of cosmic evolution. That pace matters far beyond astronomy. Galaxies are not isolated islands. Within them, stars manufacture carbon, oxygen, silicon, phosphorus, and iron. Supernovae scatter those elements into space. New generations of stars inherit them. Rocky planets eventually emerge from that enriched material. Every step depends on time. If galaxies formed earlier, stars formed earlier, heavy elements accumulated earlier, massive black holes began growing earlier. Potential planetary systems may also have appeared earlier. Suddenly, one telescope designed to observe distant galaxies begins influencing questions about the earliest possible environments where chemistry and perhaps biology could emerge. No one is claiming life existed a few 100 million years after the Big Bang. The evidence does not support that conclusion. But Webb has forced researchers to examine whether the clock governing cosmic habitability may have started ticking sooner than expected. Then another puzzle appeared. Some early galaxies contain active supermassive black holes. Not merely black holes, supermassive ones. Growing a black hole to millions or even billions of solar masses usually requires enormous amounts of time. Every stage of that growth is constrained by physics. Matter falling inward releases radiation. Too much radiation pushes additional material away, limiting how rapidly the black hole can continue feeding. This limit, known as the Eddington limit, acts like a speed restriction on growth. Yet several quasars observed at extremely early times already contain enormous central black holes. That mystery existed before JWST. Webb did not create it. But Webb is now uncovering many more candidates that help reveal how common these rapidly growing systems may have been. Perhaps early black holes formed from unusually massive stellar remnants. Perhaps dense gas clouds collapsed directly into massive seeds. Perhaps short periods of super-Eddington accretion occurred under conditions uncommon today. Each possibility carries strengths. Each also introduces new questions. Notice what keeps happening. Every apparent answer opens another investigation. That is not a weakness of science. It is often the moment when science becomes most productive. For decades, astronomers asked whether they could observe the universe's first galaxies. Now they can. The question has changed. Instead of asking whether those galaxies existed, researchers must determine why they appear so capable, so efficient, and in some cases so mature within such a narrow window of cosmic time. The telescope has not simply extended humanity's vision, it has moved the boundary between observation and assumption. Everything beyond that boundary used to belong largely to simulations. Now those simulations are being compared against reality, and reality has begun negotiating the terms of the conversation. There is another assumption quietly embedded inside nearly every discussion about the early universe. It seems almost too obvious to question. Gravity pulls matter together. Larger structures require more time to assemble than smaller ones. Therefore, the first galaxies should have been primitive, irregular systems, only beginning their long evolution. That logic still makes sense. The difficulty is that nature does not always reward intuition. One of the greatest lessons in modern astronomy is that appearance and history are not the same thing. A galaxy observed just 300 million years after the Big Bang may look surprisingly developed without having followed the same evolutionary path as the Milky Way. The resemblance can be deceptive. Two objects may arrive at similar destinations through entirely different physical processes. This possibility has become increasingly important as researchers examine Webb's earliest observations. Many of the distant galaxies attracting attention are remarkably compact. They contain enormous amounts of star formation compressed into regions much smaller than comparable galaxies in the nearby universe. Their brightness initially suggested tremendous stellar masses, but another explanation soon emerged. What if these galaxies were not unusually massive? What if they were unusually efficient? A galaxy undergoing an intense burst of star formation can briefly outshine another galaxy containing several times more stars. Massive young stars produce extraordinary amounts of ultraviolet light before ending their lives after only a few million years described. During that short period, an otherwise modest galaxy can appear far more impressive than its long-term history would justify. That realization forced astronomers to rethink one of their most familiar tools. For decades, stellar population models have allowed researchers to estimate the ages and masses of galaxies by analyzing the combined light from billions of unresolved stars. Those models work remarkably well for nearby galaxies because astronomers can compare them against independent observations. The earliest galaxies offer no such luxury. No telescope can distinguish individual stars at those distances. Everything must be inferred from blended light that has traveled for more than 13 billion years before reaching Webb's mirrors. Small uncertainties accumulate. A different initial mass function changes the expected ratio of massive stars to smaller ones. Different amounts of interstellar dust alter the observed colors. Tiny variations in chemical composition affect stellar temperatures and luminosities. The duration of a starburst changes the interpretation once again. Each assumption appears reasonable on its own. Together they create a surprisingly wide range of possible histories. That uncertainty does not weaken Webb's discoveries. It defines the frontier where observation meets interpretation. Frontiers are rarely tidy. Astronomy has crossed similar boundaries before. When Edwin Hubble demonstrated that the Andromeda Nebula was an entirely separate galaxy, humanity's understanding of the universe expanded almost overnight. Yet the observations themselves were only the beginning. Decades of work followed before astronomers understood galaxy evolution with any confidence. The same pattern repeated after the discovery of dark energy. The initial measurements suggested that cosmic expansion was accelerating. Many researchers questioned the result. Independent observations gradually confirmed it. Only then did the scientific community begin confronting the deeper theoretical implications. Discovery comes first. Understanding follows much later. Webb appears to be repeating that historical rhythm. Every new observing cycle fills gaps while revealing others that had previously remained invisible. Some candidate galaxies disappear after better measurements. Others survive repeated scrutiny. The overall picture becomes sharper without becoming simpler. Meanwhile, computer simulations have entered an unusual phase. For years, simulations acted as predictions, waiting for future telescopes. Now they are becoming laboratories for explaining observations that already exist. Researchers adjust feedback mechanisms from exploding stars. They refine how cold gas streams into dark matter halos. They improve the treatment of turbulence inside a giant molecular clouds. They incorporate increasingly sophisticated models describing radiation escaping from newborn stars. Each improvement produces galaxies that look slightly more like Webb's universe. Yet another pattern keeps emerging. Many successful simulations achieve agreement only after assuming that early galaxies formed stars with an efficiency rarely seen today. That possibility raises another question. Why would the young universe have been better at building galaxies than the mature universe surrounding us now? One explanation points toward abundance. The early cosmos contained enormous reservoirs of pristine hydrogen, flowing continuously into growing dark matter halos. Those gas supplies had experienced little disruption from previous generations of stars. Conditions may have favored sustained episodes of rapid collapse before stellar feedback became strong enough to regulate future growth. Another explanation focuses on density. The universe itself was physically smaller. Galaxies existed closer together. Gas clouds encountered one another more frequently. Interactions that are relatively uncommon today may once have been routine. The ingredients were identical. The environment was not. An ordinary recipe prepared under extraordinary conditions can produce unfamiliar results. That possibility sounds reassuring because it preserves the underlying cosmological framework. Yet it introduces a different source of unease. If environment alone changes the pace of cosmic evolution this dramatically, then much of what humanity has learned from nearby galaxies may describe only the universe's middle age. We naturally assume the present is typical because it is the only era we can observe in detail. History rarely grants that privilege. Earth's atmosphere today is not typical of its earliest history. The continents we inhabit did not always exist. Even our own solar system once looked nothing like the stable arrangement we see now. Perhaps galaxies followed a similar path. Perhaps the first billion years represented an era unlike anything that survived into the modern universe. If so, Webb is not merely photographing ancient objects. It is observing physical conditions that no longer exist anywhere within our cosmic neighborhood. That possibility transforms every distant galaxy into something more than a faint point of light. Each one becomes a surviving record of an environment permanently erased by time. And if the rules governing that environment differed even slightly from the assumptions built into our models, then the earliest chapters of cosmic history may still contain processes that modern astronomy has only begun to recognize. The telescope has given us access to that forgotten era. It has not yet translated its language. That work is only beginning. Every scientific model contains assumptions that remain almost invisible until new observations begin pulling against them. The strength of those assumptions is usually mistaken for certainty. In reality, they survive because they continue explaining the evidence better than every competing alternative. That is the position occupied by the standard cosmological model today. Its success is extraordinary. It predicts the large-scale structure of the universe with remarkable precision. It reproduces the fluctuations in the cosmic microwave background, measured to tiny fractions of a degree. It explains why galaxies cluster the way they do across billions of light years. Few scientific frameworks have survived as many independent tests, which is exactly why Webb's observations have attracted so much attention. When a successful model encounters tension, scientists do not immediately discard it. They ask a more disciplined question. Where is the missing piece? History offers countless examples. The orbit of Mercury refused to fit Newton's equations perfectly. That discrepancy persisted for decades. It was not resolved by abandoning gravity, but by discovering that gravity itself behaved differently under extreme conditions than Newton had imagined. Einstein's theory of general relativity explained both the old successes and the lingering anomaly. The anomaly was not the failure. Ignoring it would have been. Astronomy now faces a similar decision. Not because LUCDM has failed, but because Webb has illuminated regions of cosmic history where its supporting astrophysics remains incompletely understood. One possible explanation centers on something humanity cannot observe directly: dark matter. Every modern simulation of galaxy formation begins with invisible halos, composed of matter that neither emits nor absorbs light. Ordinary gas falls into these gravitational wells, eventually cooling enough to form stars. Without dark matter, galaxies as we know them struggle to exist. Yet, despite decades of experiments, dark matter itself has never been detected in the laboratory. Its presence is inferred from gravity. That distinction matters. If dark matter behaves even slightly differently from current assumptions, the earliest stages of galaxy formation could unfold in unexpected ways. Perhaps small dark matter halos formed earlier than predicted. Perhaps they merged more efficiently. Perhaps their internal structure encouraged gas to collapse faster. Or perhaps the properties assigned to dark matter particles are incomplete. None of these possibilities currently enjoy decisive evidence. They remain active areas of theoretical investigation. Notice how carefully the conversation proceeds. No serious astronomer argues that Webb has disproved dark matter. Instead, researchers ask whether observations near the dawn of cosmic history can narrow the enormous range of possibilities that still surround its nature. The telescope becomes less a judge than a filter. Each new observation removes some explanations while leaving others standing. Then another layer appears: dark energy. Today, dark energy dominates the expansion of the universe, driving galaxies progressively farther apart. But during the era Webb observes, dark energy contributed very little to cosmic dynamics. Gravity held much greater influence. That difference means the young universe evolved under conditions fundamentally unlike those surrounding modern galaxies. The balance between expansion and collapse favored rapid structure formation, perhaps more than previous calculations appreciated. Some researchers have explored whether small adjustments to the expansion history during the universe's earliest epochs might ease the apparent tension between observations and simulations. Others examine whether primordial fluctuations left by cosmic inflation contain subtle variations that produced unusually dense regions where galaxies assembled far ahead of schedule. These ideas remain speculative. Current evidence neither confirms nor excludes them. Yet their existence reveals something deeper. Webb has expanded the number of scientifically plausible questions. It has not yet reduced them to one answer. There is a tendency outside science to view uncertainty as weakness. Inside science, uncertainty often marks the edge of genuine discovery. The safest textbook answers belong to yesterday's frontiers. Today's frontier looks different, researchers argue. Measurements improve. Assumptions are revised. Competing explanations rise and fall. None of that indicates failure. It indicates that observation has moved ahead of explanation. There is another reason this matters. Astronomy does not perform experiments in the traditional sense. A chemist can repeat a reaction thousands of times. A particle physicist can collide beams, carefully control the conditions. Cosmologists cannot restart the Big Bang. There is only one observable universe. Every ancient galaxy represents a single surviving piece of evidence from an event that cannot be reproduced. Imagine attempting to reconstruct the history of an entire civilization after discovering only a handful of photographs scattered across different centuries. Every image is authentic. None tells the complete story. The challenge is not recognizing the photographs. It is understanding everything that happened between them, that is, the position Webb placed humanity in. Instead of isolated snapshots near the beginning of time, astronomers now possess dozens, then hundreds, and eventually thousands of distant galaxies spread across the first billion years after the Big Bang. Patterns begin to emerge. Some expectations survive, others weaken. A few disappear entirely. The investigation becomes statistical rather than anecdotal. And statistics carry a peculiar power. Individual surprises eventually fade. Persistent trends force explanation. Suppose future observing campaigns continue finding galaxies that consistently formed stars earlier, accumulated mass faster, and developed internal structure more efficiently than current simulations predict. The pressure on theory will continue increasing. Not explosively, gradually. Science rarely changes in dramatic moments. It changes because every new observation nudges the balance of evidence in the same direction until resisting that movement becomes harder than following it. The first years of Webb have not yet reached that point, but they have made something unmistakably clear. The earliest universe was not simply a dimmer version of the one we inhabit today. It operated under conditions whose consequences are only beginning to emerge from the data. That realization carries an implication extending well beyond galaxy formation. If our assumptions about the pace of early complexity require revision, then every later chapter built upon that timeline may deserve another look, including one question that reaches far beyond cosmology itself. How early could a universe become capable of producing observers who ask where they came from? If there is one lesson repeated throughout the history of astronomy, it is that every increase in observational power eventually changes the questions we ask. Galileo did not simply discover new moons around Jupiter. He forced humanity to reconsider Earth's place in the solar system. Edwin Hubble did not merely catalog distant nebulae. He demonstrated that the Milky Way was only one galaxy among hundreds of billions.
The discovery of the cosmic microwave background
did not merely confirm a prediction. It transformed cosmology from philosophy into precision science. None of those advances erased what came before. They expanded it. The James Webb Space Telescope appears to be following the same pattern. Its most significant contribution may not be any individual galaxy. It may be the realization that the universe reached complexity sooner than our intuition expected. Complexity is a deceptive word. It does not simply mean more stars. It means stable gravitational systems. It means chemical enrichment. It means black holes interacting with their environments. It means galaxies capable of influencing one another through radiation, mergers, and enormous outflows of gas. Each of those processes becomes the starting point for something else. The first generation of stars manufactures heavy elements. Those elements produce rocky planets. Planets create environments where chemistry becomes increasingly diverse. Chemistry, under the right circumstances, may eventually become biology. The timeline matters because every later possibility depends upon every earlier step. For decades, astronomers assumed those first steps unfolded at a measured pace. Webb has not disproved that assumption. It has asked whether the pace was faster than anyone anticipated. If the answer is yes, then another implication quietly emerges. The universe may have become capable of producing habitable environments earlier than our models suggested. That statement requires careful qualification. Habitability is not life. A rocky planet orbiting a stable star is not evidence of biology, is not evidence of intelligence. Intelligence is not evidence of technological civilization. Each transition introduces enormous uncertainty. Yet every one of those transitions also depends upon time. Time is the one resource that the universe possesses in extraordinary abundance. Move the starting point earlier, and every downstream possibility shifts with it. This is where cosmology unexpectedly intersects with one of humanity's oldest questions. If conditions favorable for planets appeared sooner, could opportunities for life also have appeared sooner? No telescope has observed such worlds. No observation suggests civilizations existed a few 100 million years after the Big Bang. The evidence goes nowhere near that far. But the discussion itself has changed. The earliest galaxies are no longer viewed merely as archaeological curiosities. They define the opening chapters of every later cosmic history, including our own. That realization also changes how we think about ourselves. Human civilization often imagines itself arriving relatively early in cosmic history. On everyday timescales, that feels reasonable.
The universe is 13.8 billion years old.
Earth formed roughly 4.5 billion years ago. Complex multicellular life occupies only a tiny fraction of that history. Modern civilization occupies an almost immeasurable instant. Yet Webb reminds us that the first billion years may have unfolded far more rapidly than expected. If galaxies matured efficiently, if stars formed abundantly, if heavy elements accumulated quickly, then the universe may have begun building the ingredients for future complexity long before Earth even existed. That thought carries no dramatic conclusion. It carries perspective. Our planet is not merely separated from the Big Bang by billions of years. It is separated by countless generations of cosmic construction that began before the Milky Way resembled anything recognizable today. There is another consequence that receives less public attention. Astronomers often describe observations as looking back in time. Strictly speaking, they are looking through time. Every distant galaxy sends information that has traveled uninterrupted across expanding space for more than 13 billion years. No archive on Earth preserves history so directly. Every photon entering Webb's detectors left its source before the Sun existed, before Earth existed, before the atoms making our bodies had been incorporated into a planetary system. Those photons survived every intervening event, the rise and death of stars, the collisions of galaxies, the formation of clusters, the expansion of space itself. Only now do they complete their journey. That means Webb is not creating ancient history. It is receiving messages that have been in transit since the beginning of cosmic structure. Each observation is less like taking a photograph and more like opening a letter delayed for nearly the entire lifetime of the universe. Some letters confirm what we expected. Others reveal details the sender never intended to surprise us with. The difficult part is deciding whether those surprises belong to the message or to the assumptions we brought while reading it. That distinction defines the current state of cosmology. Researchers are not choosing between confidence and doubt. They are deciding which assumptions deserve the greatest scrutiny. Perhaps improved simulations will eventually reproduce every apparent anomaly. Perhaps future observations will reduce today's tensions to ordinary statistical fluctuations. Or perhaps Webb has exposed a genuine gap in our understanding of how the first structures emerged from the aftermath of the Big Bang. The evidence has not delivered its final verdict. It rarely does this early, but something has already changed. For decades, the earliest universe existed largely inside equations. Today it exists inside observatories. And once observations begin replacing assumptions, history has shown that the universe often proves less interested in meeting our expectations than in quietly replacing them with something far more difficult to ignore. There is a temptation to think that the James Webb Space Telescope will eventually answer all of these questions. History suggests something different. Every great observatory has reduced uncertainty in one place while creating it somewhere else. That is not because the universe becomes more mysterious as technology improves. It is because better observations expose us assumptions that previously had no opportunity to fail. Webb has done exactly that. Not by overturning modern cosmology, not by proving that the Big Bang model is wrong, not by demonstrating that dark matter does not exist. Its achievement is more subtle. It has shown that the opening chapters of cosmic history contain more complexity than our previous observations allowed us to see. That difference matters because cosmology is built from two kinds of knowledge. There is the universe we observe, and there is the universe we infer. For years, the earliest few 100 million years after the Big Bang belonged mostly to the second category. The equations describing gravity, dark matter, and cosmic expansion could be tested indirectly, but the galaxies themselves remained almost invisible. Simulations filled the gaps where observations ended. Now those gaps are shrinking. Every new observing campaign adds another collection of galaxies. Every spectroscopic confirmation replaces an estimate with a measurement. Every revision to stellar population models reduces one uncertainty while revealing another. The balance is changing. Observation is steadily taking territory away from inference. That transition carries consequences extending well beyond astrophysics. Human beings naturally build stories from incomplete evidence. We always have. Ancient civilizations looked at the night sky and imagined familiar patterns because the mind is remarkably skilled at connecting scattered points into coherent pictures. Science does something different. It accepts that many of those connections may be temporary. Every explanation survives, but only until a better explanation accounts for more of the evidence. The remarkable strength of modern cosmology is not that it claims perfection. It is that it has repeatedly survived opportunities to fail. The cosmic microwave background could have contradicted it. It did not. Large-scale galaxy surveys could have disagreed with its predictions. They largely did not. Gravitational lensing measurements could have revealed an entirely different universe. Instead, they reinforced much of the existing framework while exposing new puzzles at smaller scales. Webb belongs within that tradition. Its discoveries are not isolated acts of rebellion against established science. They are stress tests. Some assumptions have emerged stronger. Others have begun to bend. A few may eventually require replacement. No one yet knows which category today's tensions will ultimately occupy. That uncertainty is not disappointing. It is extraordinarily valuable. Because unanswered questions identify where progress is still possible. Consider what humanity has accomplished in little more than a century. We moved from debating whether other galaxies existed to measuring objects whose light began its journey before the Milky Way had fully assembled. We developed detectors capable of identifying chemical signatures across more than 13 billion years of cosmic expansion. We transformed faint infrared photons into evidence capable of testing ideas about the earliest structures ever to exist. From the perspective of human history, that progress borders on the unbelievable. From the perspective of the universe, it is almost unimaginably recent. The oldest galaxies Webb observes had already completed much of their early evolution before Earth itself formed. Our entire biological history occupies only the closing pages of a timeline those galaxies witnessed from the beginning. Seen that way, another possibility quietly emerges. Perhaps the greatest limitation in cosmology has never been mathematics, nor telescopes, nor computing power. Perhaps it has been perspective. Every generation assumes the observable universe available to it represents something close to the complete picture. Every generation eventually discovers another horizon. The horizon moves, the questions move with it. That may be the deepest implication of Webb's first discoveries. Not that our current models are collapsing, not that the universe has become stranger overnight, but that reality continues extending beyond the point where certainty feels comfortable. There is something profoundly revealing about that pattern. The farther back we look, the less the universe resembles a simple beginning, waiting patiently to be explained. Instead, it resembles an ecosystem already in motion, filled with processes interacting at speeds we are only beginning to understand. the earliest galaxies no longer appear as faint previews of everything that followed. Increasingly, they look like active participants in a history that accelerated almost immediately after the first stars ignited. Whether future observations ultimately confirm that impression or soften it, one fact is unlikely to change. Humanity now possesses the ability to watch the universe emerging from its own infancy. That opportunity carries a quiet responsibility. Every unexpected observation should be met with discipline before excitement. Every successful theory deserves respect before replacement. Every anomaly deserves investigation before dismissal. Because the history of science has rarely advanced through certainty alone. It has advanced by recognizing the moment when evidence begins asking questions that our assumptions can no longer answer. The James Webb Space Telescope has not delivered the final chapter of cosmic history. It has simply allowed us to read the opening pages with enough clarity to realize they were never as familiar as we believed. And if the beginning of the universe still has the power to surprise us, after decades of increasingly precise science, then the most unsettling possibility is not that we have misunderstood the cosmos. It is that the universe has always been more capable of building complexity, sooner and more efficiently than our imagination was prepared to allow.